Okay, so we're just going to look at some setups here and not really evaluate the integrals, just because we can talk about techniques of evaluating integrals later, but I'm going to just assume that you can evaluate any integral at this point. So, all right, so for area, we know that it's simply just straight up the integral from a to b of the upper function minus the lower function. Nothing really fancy about that. In contrast to volumes, where of course we have to play a little bit of a game with it. So we really just need to figure out where we are beginning our integration, and clearly that's 0 here. And where are we ending it? And that's not so obvious, but we would figure that out by equating these two functions and seeing wherever they intersect. So we would solve cosh of x equal 3 e to the negative x. So of course, to solve this equation, we need to know the definition of cosh, which every good calculus student should know. There we are. So now we're going to solve for x. Okay. Well, let's get rid of that 2. So we have e to the x plus e to the negative x is equal to 6 e to the negative x. And if we just multiply everything by e to the x, we will really clean it up. So multiplying each term by e to the x will give us e to the 2x plus 1 is equal to 6. So we get e to the 2x is equal to 5. And so if you solve for x, you're going to get 1/2 ln of 5, or ln of rad 5 if you wish. Very good. So that means that our area is the integral from 0 to 1/2 ln 5 of the upper function, and we can see that that's 3 e to the negative x, minus the lower function, which is cosh of x dx. Okay, now let's just change the problem a little bit and have a conversation about it. Suppose we were told to integrate from 0 to, I don't know, let's just say that 10 is out here somewhere, safely far away. And let's say we actually wanted this whole area here of this sort of bow tie shape. Well, we would, of course, still have to figure out that intersection point, which we know to be 1/2 ln of 5. And we would integrate from 0 to 1/2 ln of 5, with the upper function being 3 e to the negative x and the lower function being cosh. But now we'd have to add the integral from 1/2 ln 5 to 10, okay, with the upper and lower functions reversed, because now for this portion of the graph, cosh is the upper function and 3 e to the negative x is the lower function. So in that case, we would now just add the 1/2 ln 5 to 10, and now it's cosh as the upper function minus 3 e to the negative x as the lower function. All right. Okay, and then there were volume integrals, and probably remember that these were a lot more complicated to set up than just area ones. Mainly, there were actually two different entire techniques for setting them up. There were the shells method and the discs or washer method. So the washer method, I'll just remind you of the two looks of them. The washer method is that the volume is from a to b of pi times capital R squared minus little r squared dx. I'll just assume we're integrating with respect to x for these formulas. And so this would be like the outer radius, and this is the inner radius of the revolution. Okay, and of course it was called the disk method when that little r was equal to 0, and you just had pi times capital R squared. Then we had the shells method, cylindrical shells. which was 2 pi RH dx. And here, this is the radius. Okay. And h was the height of the shell. All right, and r and h both would depend on x. So let's see what we have in this situation. Okay, so the idea here is that while it seems like we have some choices to make, really the only choice that we're making is what's the best way to integrate this, dx or dy. And in this particular one, clearly we could choose dx or dy, right? Because if we're integrating dx, it means that our sample rectangle of integration would look like this, and the d whatever the variable is the tiny dimension. So this is small x values, right? Small horizontal length. So clearly we have a very nice beginning, which would be 0, a very nice end, which would be whatever that x value is there. It looks like ln of 4. And then we can go ahead and set up our problem. Alternatively, we could have decided instead to integrate this with respect to y, and actually that would also be very easy because we have a very nice start. 1 and 4 would be the beginning and the end of our integral here. Let's stick with dx for now. Okay, so now that we've settled on dx, we look at our axis of rotation and visualize what shape will get formed by rotating that rectangle around. And in this case, we are going to get actually a disk. All right, if you rotate that particular rectangle around, you're going to get a disk shape, which means we are using the washer method. You can also think of this as the sample rectangle is perpendicular to the axis of rotation, so that's perpendicular, right? That was the shortcut, versus being parashell in the other case. All right, so let's set this thing up. So we know we're integrating dx. That's the only decision we've made so far. That means that these bounds on the integral must be x values. And so we can see that x starts at 0 and ends at ln of 4, okay, which you can solve by solving e to the x equal 4. We know that we are using the washer method. Well, indeed, the disk method here. So it's going to be pi r squared. So the only thing we need here is capital R. All right, well, capital R is this measure here that is read from the axis of rotation to the end of our rectangle. So we can see that capital R is going to be 4 minus the height of the function, e to the x. Okay, so it's 4, which is this entire distance here, minus the height to the function. So that would be 4 minus e to the x. So our total setup would be 0 to ln 4, pi times 4 minus e to the x, quantity squared. All right, now let's talk about how we might have set this up if we'd opted to integrate with respect to y. So let's suppose everything about this problem is the same, but now we are choosing to integrate with respect to y. So we're going to integrate dy. And now if you take this purple rectangle and rotate it around the axis of rotation, you're going to get a shell shape object. Okay, so we will set this up as shells, and we know that this is going to be y values c to d, and we're integrating dy, and we know we're using the shells method, so that's 2 pi r and h, and all we need to do is figure out what r and h are. Okay, well, r here is, of course, this length right here. It is the distance from the axis of rotation to the specific rectangle that we're interested in. Okay, so it's going to be, also, again, 4 minus whatever this length is here. All right, now that is our floating variable. That's y. Y, which marches from 1 to 4, okay? And our radius at any given y value is going to be 4 minus y. Okay, and what's our height? Well, our height is the height of the cylinder, which in this case is a horizontal length. Okay, so what is the height here? Well, it's actually just x. Okay, this horizontal distance is x. It's very hard to see what I just drew, but this horizontal distance here is x. So what is our height? Our height is x. However, we're integrating dy, which means we can't just leave x in our integral. We need to convert x over to y's. Well, no problem. We have the curve. So we know that x is equal to ln of y. So our whole setup would be the integral from y beginning at 1 and ending at 4, 2 pi times 4 minus y times h, which is ln of y, dy. Okay, let's talk about integration by parts, which was definitely featured on the first exam. Integration by parts is particularly nice when, of course, you can't see a substitution, which you should always look for at the beginning. And you have either inverse trig functions or natural logs. Those are really strong signals that integration by parts ought to be considered. So here we have an inverse trig function. So let's use integration by parts. And we're going to let u equal inverse tangent of x. So its derivative is 1 over 1 plus x squared. And you do need to know those derivatives of the inverse trig functions, of course. You needed to know them coming into this class. So dv is everything we did not choose for u, so that would simply be dx, and v is therefore equal to x. Okay, so our integral here becomes uv minus v du, right? Ultraviolet voodoo. So that would be x times inverse tangent of x minus x over 1 plus x squared dx. And we've punted to a new integral that we need to work out. And this one can be done by u substitution. All right, so simply let u equal the denominator. And we can see that this whole thing is x times inverse tangent of x minus 1/2 and x dx. So we have du over u. So this is going to be x times inverse tangent of x minus 1/2 ln of the absolute value of u plus a constant. That constant's needed. We unwrapped our last integral here. So all we have to do is convert u back over to x's. And since 1 plus x squared is naturally a positive expression, the absolute value bars are unnecessary. So there we go. Okay, let's look at an integration by parts problem with bounds on it. Okay, now my recommendation for integration by parts with bounds is that you actually work this out as side work without bounds and then finish with the fundamental theorem of calculus. Okay. If you do include the bounds, then you need to track them all the way down the line. And with integration by parts, that can be particularly annoying because half of the terms are already integrated. So you're at the stage where you're plugging numbers in and half of the terms haven't been integrated yet. And for heaven's sake, what if it's a boomerang integration by parts? And with bounds, that can be very difficult to manage. So side work, just work out the entire antiderivative as an indefinite integral. Okay, so there's a couple ways you can approach this. First, you can do a u substitution to clear out that natural log, but since it was suggested just to go right in and do integration by parts, let's go and do that right now. So here we're going to let u be ln of x squared. So du is going to be 2 ln of x over x dx. And dv is dx, so v is equal to x. So applying the ultraviolet voodoo here, we have x times ln of x quantity squared minus v du, so the x's cancel, and we actually just get 2 ln x dx. Okay, now it would benefit you to know the antiderivative of natural log here, which is x ln x minus x. However, if you don't know it, you can just do another round of integration by parts on this guy. So we can just say, well, u is equal to 2 ln x, or you could factor the 2 out before you start. Doesn't really matter. All right, so where does this leave us? We have now x times ln x squared minus, and now another round of ultraviolet voodoo. So this will be 2x ln x minus antiderivative of x times 2 over x, which is just 2 dx. Very good. We can now integrate that 2, I hope. So this is something like this, minus 2x ln x. The negative distributes, of course, and then we just get 2x plus a constant. All right. Now, we haven't answered the original question. We just found the antiderivative of integral of ln of x quantity squared. So now we can answer the original question by using the fundamental theorem of calculus. So that is equal to this whole thing from 1 to e. So we plug e in there, and we're going to get e times ln of e, which is 1 squared, of course, minus 2e plus 2e minus, now we'll plug 1 in, so we get 1 times ln of 1 is 0. So in fact, any term that has an ln of x in it here will just go to 0. So that just leaves us with a 2 times 1. So we get e minus 2 is our final answer. So this one suggested that you begin with a substitution followed by integration by parts. The suggested substitution was w equal e to the x. Okay. And the most common way that this was done incorrectly was to convert this to w squared sine w dw. And if you're looking at this and you don't quite see why that's wrong, then you need to practice your u substitutions, because this is a very common rookie mistake with substitutions. Okay. The issue here is that dw is e to the x dx, which means that one of the e to the x's here, remember there are 2 of them, this is e to the x times e to the x, and one of them gets reserved with the dx and becomes dw. The other one survives. So what this really is think of it as w squared sine w, but let's carefully track that dx. Dx is dw divided by e to the x, which is w. So this is just w sine w dw. Okay, and again, this was a very common mistake on exam 1. So The rest of this can be finished with integration by parts, and I'm actually not going to go and do that because that's about as vanilla as integration by parts gets from that moment on. But please be careful with your transitions from dx to du or dx to dw or whatever whenever you're doing a substitution with an integral. You have to track those factors carefully. All right. Since we can't immediately think of what might be the antiderivative of this, we should try to play around a little bit with it. And cotangent, we know we can turn into cosines and sines. And in terms of derivatives, cosines and sines play really well with each other. So I think that's a good direction to take this. And that would give us cosine cubed over sine. Okay. But this one itself isn't particularly straightforward. But you do know from section 7.2 that if you have an integral with a bunch of cosines and sines, you should try to reserve one of the factors, either cosine or sine, and then try to turn whatever's left into the other. So if you reserve a cosine, whatever's left should be turned into sines. And if you reserve a sine, whatever's left should be turned into cosines. Now, we can't reserve a sine because that's in the denominator here, so we'd really be reserving a cosecant. That's not a direction we want to go in. So can we reserve a cosine? Well, if we did, we'd get cosine squared over sine times cosine of x dx. So there's our reserved for du. And now we just have to find some way of converting everything on this side here into sines. Convert to sine x's. Okay, so that we can let u equal sine of x and just have something purely algebraic at that point. Well, if you reach deep into the corpus of your trigonometric knowledge, you may come up with a trig identity that relates cosine squared to sine squared. Perhaps this one. All right, now we can let u equal sine of x, and perfect du is cosine of x dx, exactly as we wanted. So this becomes 1 minus u squared over u du, which at this point is 1 over u minus u du, which integrates to ln of absolute value of u minus 1/2 u squared plus c. And you can just finish by converting everything back over to sine. So we get ln of absolute value of sine minus 1/2 sine squared of x plus c. And there we are. Okay, it's time to talk about trigonometric substitution. Yeah, so first of all, the thing we need to deal with is this 4. Wouldn't it be nice if we just had a u squared and this were 9 minus u squared? Well, we can create that by just saying, well, we want u squared to be 4x squared. And taking the square root, we can see we want u to be 2x. Well, that's our substitution. So du will be 2 dx. And that means that our integral is going to be 1/2 times the square root of 9 minus u squared du. Okay, very good. Now we can invoke the trigonometric substitution needed. We know in this particular case that if we let u equal 3 sine of theta, that's going to give us what we want. So du is, in this case, 3 cosine of theta d theta. So let's go back to our integral and see what happens. Well, we're going to get a 3/2 times 9 minus 9 sine squared theta. And our du is, well, I already put the 3 in, so this is cosine of theta d theta. Okay, Now we can factor the 9 out of the square root, which comes out as a 3. So we get 9 over 2 times 1 minus sine squared times cosine theta d theta. And of course, that whole part there, 1 minus sine squared, is just cosine squared under the radical, which is cosine. We got another cosine in there. So this becomes 9/2 times cosine squared theta d theta. Okay, well, how do we integrate cosine squared? Well, that should be fairly fresh in your memory because of chapter 10, polar integrals, which often produce terms that look like that. So we know that cosine squared becomes 1/2, so I'll write this as 9/4, 1 plus cosine of 2 theta. And we can distribute the 9/4, so we get 9 over 4 plus 9 over 4 cosine of 2 theta d theta, and we can now integrate, giving us 9/4 theta plus 9 over 8 sine of 2 theta plus c. All right, but we need to convert back over to x's, actually through u, right? So we know from our substitution that u is equal to 3 sine theta. Okay, so sine of theta is u over 3. And let's draw a triangle here. And using SOHCAHTOA, we'll label the opposite side u and the hypotenuse 3. The missing side down here will be 9 minus u squared under a radical. So now we can read the information we need off of the triangle. However, sine of 2 theta is not directly on that triangle. No problem. We'll use an identity. 9 over 8 times 2 sine theta cosine theta, so that'll be 9 over 4 sine theta cosine theta plus c. And now we can read off everything we need. So this is 9 over 4 times inverse sine of u over 3 plus 9 over 4 sine of theta, which is directly just u over 3, times cosine of theta, which is rad 9 minus u squared over 3. And if you recall, u was equal to 2x, so this is 9 over 4 times inverse sine of 2x over 3 plus, well, we're going to get some major cancellation here. The 9 cancels with 9, and remember, u is 2x, so 2x over 4 is just x over 2, so we'll just write 1/2 x times radical 9 minus 4x squared plus c, of course. Okay, here was another trig substitution problem. So this was the integral from 1 to 2 of rad x minus 1 over x. And it did not look like a trig substitution problem right away, but you were suggested in the problem statement to begin with x equaling u squared. So dx would be 2u du. And let's see what happens. So this would be the integral, worry about the bounds in a second, of u squared minus 1 over x, which is u squared, and dx, which is 2u du. And now when x is equal to 1, u is equal to 1. And when x is equal to 2, u is equal to rad 2. All right, and we can cancel a u factor, so what we have is the integral from 1 to rad 2 of 2 times rad u squared minus 1 over u du. Okay, and now this does look like a trigonometric substitution problem. And in this case, we would let u equal secant of theta. So du is secant of theta, tangent of theta, d theta. And let's see what that turns our integral into. So we would get 2 times secant squared theta minus 1 over secant of theta, and du is secant of theta tangent of theta d theta. And what about our bounds? Well, those are u values here. So when u is equal to 1, theta is whatever angle has a secant value of 1, which would be 0. And when u is rad 2, theta is whatever angle has a secant value of rad 2, which would be pi over 4. Okay, a nice thing about updating our bounds here is that we never have to go back to u and then back to x. We're just going to keep working this out until we get our answer. So, all right, let's clean this up. The secants, of course, cancel, and all of that radical nonsense just becomes ultimately a tangent. So then we have another tangent making tan squared. So this is 2 times tan squared theta d theta. Okay, well, how do we integrate tangent squared? Well, it's easier to write that as secant squared minus 1, because we know how to integrate secant squared. So this becomes 2 times tangent of theta minus theta from 0 to pi over 4. So plugging pi over 4 in, we get 2 times tangent of pi over 4, which is 1, minus pi over 4. And plugging 0 in, we get 0 minus 0. So our final answer is 2 minus pi over 4. All right. All right, let's talk about improper integrals for a little bit. So as you know, there are many forms. This is probably the most basic one that we have right here. This wasn't on an exam. I just wanted to warm us up with this one. With an improper integral, you basically need to identify where there's anything that's bad. So it could be either bound might be bad, or there might be something bad within the interval of integration. So in this vanilla case here, what's bad is that infinity, and anything that's bad needs to get managed. So if we have that infinity, we would need to turn this into a limit problem as t approaches infinity of now the integral from 0 to t of e to the negative x dx. And all we have to do is just work out this integral here, and it's not going to have an issue because we're presuming that at any given t value this integral exists, right? 0 to a million, we're fine. 0 to a billion, we're fine. So we work this out in terms of t, and then we take the limit as t goes to infinity, and there we are. That gives us the infinite integral. Okay, now what if we have badness at both bounds? So for instance, negative infinity to positive infinity of something like 1 over 1 plus x squared. Okay. Well, in this case, you have no choice but to split it in two integrals. So you just have to choose a good guy somewhere in the middle, like 0. And you integrate from negative infinity to 0. And then you integrate from 0 to infinity. And, okay, well, that was a little bit of a punt, but we're not really done setting up the problem because we still have two separate improper integrals. The only thing is that at least each of those now only has one bad guy. So in this one, we would let the limit as t approach negative infinity, t to 0, and work that out. And then you would add this limit 0 to t. Okay, and typically, in terms of actually working these out, I'd probably work each one out independently and then add the answers together. Okay. However, these are both going to equal the same thing because this is an even function. So you could take advantage of some symmetry in this particular example, but not always. negative pi over 2 to positive pi over 2 of tangent of x dx. And this is a situation where we have bad behavior at both ends. So bad guy here and a bad guy there. All right. So what we needed to do was pick a good guy in the middle, and 0 is a great pick. So we set our limit. However, these are one-sided limits. Now with infinity, you don't need to specify, because with the infinity examples, you can only approach infinity from one side, right? Obviously. And same with negative infinity, you can only approach that from the right. So, however, here we do need to specify that we are approaching negative pi over 2 from the right. And when we add this one, we are now approaching positive pi over 2 from the left. Okay, so we do need those little pluses and minuses. So as a rule of thumb, if you're setting up an improper integral and you're writing out the limit, if the bad guy occurs at an upper limit of integration, you have to approach that limit from the left. And if the bad guy was a lower limit of integration, then you approach that from the right. So you're always approaching from inside the interval. Okay, so you approach lower bounds from the right, you approach upper bounds from the left. Okay, sometimes you can have something bad go on in the middle of the interval. So let's make one up like that. How about 0 to 2 of dx over, say, x minus 1. Okay, this integral looks quite harmless, except for the fact that something horrible happens right at x equal to 1, which is right in the middle of this interval. So we would really have to say, well, this is like integrating from 0 to 1 plus integrating from 1 to 2. And each of those are still improper with a bad guy. Here the bad guy is the upper limit, and on that one the bad guy is the lower limit. So now we can write this as a limit. So we can say limit as t approaches 1 from the left of 0 to t, plus the limit as t approaches 1 from the right of t to 2. Okay, and that one's handled. Now let me just give you one more even worse situation. How about we go to 0 to 2 again, but this time x minus 1 in the denominator. So now 0 is bad and 1 is bad. Okay, so no problem. We can still sort of start the same way. We'll go from 0 to 1, dx over x minus 1, plus 1 to 2. So we're splitting over one of the bad guys. We're kind of ignoring for the moment that 0 is also bad. But let's keep track of what's bad. Right now, the 1 is bad here. So on that integral, we would just need to quickly convert to a limit from the right. On this one, both 0 and 1 are bad. So that one further splits, and we need to pick something between 0 and 1 to split around. So how about 1/2? Okay, now we're ready to turn it into limits once each integral has no more than a single bad guy anywhere. So here we have a bad guy, but 1/2's okay. Here we have the 1 is bad, and here we have the 1 is bad. So we are ready, and there's no more bad guys in any of the middles. So we're ready to write this as a sum of limits. We can say limit as t approaches 0 from the right of t to 1/2 limit as t approaches 1 from the left and finally limit as t approaches 1 from the right And then, of course, for this one as well, I would probably call it A, B, and C, work out all of them. And if any one of those pieces was a divergent integral, then you get to conclude that the whole original integral diverges. But if they all converge, then the original integral converges, and the answer is just the sum of whatever everything worked out to. Okay, let's talk about arc length and surface area for a minute, in Cartesian coordinates, of course. So we know the arc length formula in Cartesian coordinates is this guy. Okay, structurally very similar to the arc length formula we recently saw in parametric curves. Okay, find the arc length of this function here. Actually, you were just asked to set it up, thank goodness, because this one would have been eminently difficult to work out, if not impossible. So of course, we are just going to work this out from 0 to 1, and we get 1 plus the derivative of 3 to the cosh, which is 3 to the cosh, times ln of 3 times the derivative of cosh, which is sinh, and that all is being squared. And there we are. There's our setup. Simple as that. Okay. Now, what about surface area? Well, the formula for surface area is very similar to the formula for arc length. However, there are a few things to consider. For instance, you could be rotating around the x-axis or rotating around the y-axis. So we would integrate from, say, a to b or c to d or whatever, I don't care, okay, of 2 pi times, now what goes right here is either x or y. So you would put an x if you're rotating about the y-axis. You'd put a y there if you're rotating about the x-axis. Okay, followed by 1 plus, and then I'm going to put just dy dx squared and a dx. However, if we were integrating with respect to y, then you would put a dy here, and you would put dx dy there instead of dy dx. Okay, so in other words, whatever this differential is must match the denominator differential within the square root here. Okay, find the surface area here of y equal 1/3 x cubed, and the bounds you were given were 0 to 1. Okay, and we're rotating about the x-axis. All right, so that means our surface area formula would be 0 to 1, because we're going to integrate dx, 2 pi times, well, since we're rotating about the x-axis, this would have to be a y right there. 1 plus the square of dy dx. So dy dx, we can see, is actually just x squared. So that would get squared again, so x to the 4th dx. Okay, now we're not done our setup, but this letter here has to be converted to the letter that we are integrating with respect to. So if that already were an x, for example, if instead of rotating around the x-axis, we were actually rotating around the y-axis, then we would put an x here. And great, our whole integral is now set up because everything's in terms of x and we're integrating with respect to x. However, since that's a y here, we need to actually convert that y into x's. And y was given as 1/3 x cubed. Okay, we're not going to work out this whole surface area, but that's just a u substitution, of course, because derivative of the inside of that radical is right on the outside there.